won't because it just goes too late for me. But I appreciate hearing anything and not panel discussion.
Get out of your way.
So let me remind you that we were in the middle of proving this theorem that a Coxeter group is finite if and only if the associated bilinear form is positive definite. And we proved one direction last time. We proved that if you have a positive definite bilinear form, then you're finite. Okay. And so for the next two classes, we're going to be talking about the other direction. So we're going to be proving that if we have a finite Coxeter group, then this group has a positive definite bilinear form. Okay? And today, we're going to start by building up a little bit of theory. So this is fun because we're going to get to learn a little bit of representation theory. That's what we're going to need to prove this other direction. And so that's what we're going to do today. Representation theory. So let's learn some basic things about representation theory. First of all, what is representation theory about? It's about group representations. And a representation of a group G is simply a homomorphism from our group to a general linear group. Some vector space B. Okay, so that's our main definition. And we're used to seeing this. You see, I kept talking about that. We have talked already about what I call the geometric representation of a Coxeter group. And that was a homomorphism from G into a general linear group. Okay? And an arbitrary representation is just any homomorphism of this form. Now, how should we be thinking about this? Well, the idea is just that this is going to be a way of thinking of each one of our group elements as an invertible transformation, an invertible linear transformation on V. Okay? So this is a way of representing group elements by invertible linear transformations. And we know that if maybe you're more comfortable with invertible linear transformations once we choose a basis for V, because once we choose a basis for V, then a linear transformation is just a matrix. And so you're just going to think of your group as being represented by matrices. So, or invertible matrices if we choose a basis for V. Okay. In other words, a very simple way of describing this is you want to find a matrix for each group element so that the matrices exactly have the relations that the group is supposed to have. So we have seen group representations already. Let's talk about a group representation of the symmetric group S3. So we need to find a homomorphism from S3 into something. Okay. Now, again, let's think that we already have a basis here, and so we want to think of permutations as being represented by matrices. Okay? And you guys are already very familiar with a way of representing a permutation by a matrix. It's what's called a permutation matrix. Right? So, for example, the permutation matrix of 1, 2, 3 is the matrix 1, 1, 0, 1, 1, 1 was the identity matrix, right? Well, etc. So 1, 3, 2 goes to 1, 3, 2. To 1, 3 goes to 2, 1, 3. 2, 3, 1 goes to. Here we kind of have a choice, you see, because we can choose to use these as rows or columns. Okay, so I'm going to represent this as the first row has a 1 in the 2 position, the second row has a 1 in the 3 position, and the third row has it in the first position. Okay. So 3, 1, 2, and 3, 2, 1. Okay. So there's a group representation into, let's say, C3. Okay. So what does it mean that we're thinking of each group element like 2, 1, 3 as multiplication on the left by this matrix? Okay. Now, what does this need to satisfy? Well, it needs to satisfy that, for example, where's the transposition? So this is a transposition, right? 2, 1, 3. So as a group element, this thing squared is the identity. And so it better be true that as a matrix, this thing squared is the identity. Okay. Or, for example, if you multiply a group element times a group element and you get another group element, then that better be true also for the matrices. That's a group representation. Okay. So you see these group representations are not anything too mysterious. So let's prove some facts about group representations. Okay. Let's say that we have a finite group, and let's say that we have some representation of it. Okay. Then I claim that there is a positive definite bilinear form on V, which is invariant under the action of G. So we'll see in a second what this means. So what does this mean? We need a bilinear form on V, right? So I just need to tell you how to take the inner product of two things in V. And I have two requirements. First of all, that's positive definite. And second of all, invariant under the action of G. And so what this means is simply that if you act with a group element on both sides, then you're going to get the same answer. Okay? For G in your group and U and V in V. Okay? But let's think about this carefully, because where do I need my group representation here? And this is one of the conditions. And you see the way that this is defined, what does the symbol mean? G acting on U. Well, the thing is that U is a vector in V, and G is a group element, which we are thinking of as a linear transformation on V. Okay? And so my group element takes some vector of V and sends it to some other vector of V. So when I write something like group element times vector, then implicitly I'm doing this using this representation. Okay? Now, in symbols, what I'm saying is that the way you're supposed to think about this is that G really corresponds to rho of G is some invertible linear transformation, and that thing, which you, if you want, you can think of as a matrix, acts on U. Okay. But if I write this every time I'm going to say this, you're going to get really confused by the notation. And so let's just agree on this notation, that this is the standard notation. G acts on U. Okay. So there's my first lemma. Okay. So proof. First, let's ask ourselves a simpler question. If I forget about this business of being G invariant, which is that's a short way of saying invariant under the action of G, G invariant. If we forget about that, is there a positive definite bilinear form on V, period? Well, this is actually a pretty simple question because V is just some vector space, right? And you're free to choose a bilinear form on it. Okay? And so what you can do is just say, well, pick a basis, make it orthonormal. And that's going to be positive definite. You're just saying, put the yeah, I mean, just do that. So that means that we can definitely have some positive definite form on B. And now, what I'm going to do is take this positive definite form and pull off some trick where I'm going to take this thing and make it invariant under G. Okay. And what I'm going to do is the following. I'm going to define a new positive definite bilinear form in terms of this one. Okay. And what I'm going to do is the following. The new inner product of U and V is going to be the following. It's going to be the sum over all the group elements of G acting on U, comma, G acting on V. I'm going to define this, and I'm going to show to you that this is positive definite and this is invariant under G. Okay. So why is this positive definite? Well, that's easy because to check whether you're positive definite, you have to prove that this is positive if U is not 0. But by definition, this is equal to this. Right? And we know that this one is positive definite. Okay? And so this will be non-zero if G acting on U is not 0. So the question becomes, is G U 0? Well, first of all, so U is not 0. Okay. So can GU be 0? Well, it can't be because G is an invertible transformation. And an invertible transformation can't send something that is not 0 to something that is 0. So that means that this is not 0. And because this round bilinear form is positive definite, each one of these things is positive, which means that the whole thing is positive. So, I mean, it makes sense because I'm just adding positive definite things, so this is still going to be positive definite. The key thing is G invariant, and this is very cute because what I have to do now is prove that U and V have the same product as a group element times U, comma, a group element V. So let's take some group element H, and let's compute HU, comma, HV. Okay? So let H be some group element, and U, V, and V. I'm supposed to prove to you that this is equal to U, comma, V. Okay? So what is this? By definition, this is summation over elements of the group of G times H times U, comma, G times H times V. But the nice thing about this is that H is some fixed group element, right? G is ranging over the whole group. So as you fix a group element and multiply it by all the different group elements, what are you going to get? Well, basically, this G times H is going to travel around the whole group and hit every group element exactly once. Right? And this, by definition, is U comma V. That's kind of cute. One way of thinking about this is that you're kind of averaging over the group. So you want the inner product of U and V, and you kind of want to take it to be the average of what it is as you range over the whole group, and that's what makes this G invariant. Okay? So that proves my first lemma. Okay. Okay. So let us talk about some more definitions. So, definition. Let's say that a group representation is irreducible if the following holds: if V has no proper subspace U, which is G invariant. What do I mean by this? Well, the group elements act on V, right? Each group element moves V around. Okay? To be G invariant means that you have some subspace such that the group elements send vectors in U to vectors in U. In other words, G acting on U is a subspace of U. Okay? And I think that the best way to understand this is with an example. Okay? So let's figure out whether this group representation right here is irreducible or not. So what do we have to do? We have to figure out if C3 has, if we can find a subspace of C3 so that each one of these group elements fixes that subspace. Okay. Now, what's a subspace of C3? A proper subspace? It's either a line or a plane. Okay. So we either have to find a line such that each one of these guys fixes the line, or a plane such that each one of these guys fixes the plane. Okay. Now, we understand what these operations are actually, because, for example, what does the group element 2, 1, 3 do to the vector A, comma, B, comma, C? Well, these are column vectors. It multiplies A, B, C by this thing. When you multiply it, you get B, A, C. Right? What does 2, 3, 1 do? It gives me B, C, A, etc. Okay? So we understand how this group acts on the three-dimensional space. The group element 2, 3, 1 sends me to, puts the second coordinate, the third coordinate, the first coordinate, etc. Okay? So the question becomes, can you find, for example, can you find a vector such that when you multiply it by any one of these things, you get the same vector back? What do you guys think? I think you can. So I think there is a vector so that no matter which one of these matrices you multiply it by, you get that vector back. You see, what do you need? Well, if this group element is going to send this thing back to this one, then A has to be equal to B. If this group element is going to send this one equal to this one, you're going to have A equal to B, B equal to C, C equal to A. And then you say, okay, well, that must be a vector that has all three coordinates equal to each other. And then when you think about it, well, each one of these group elements just kind of moves the coordinates around. And so if you start with a vector x, comma, x, comma, x, these group elements don't touch it. Okay? So in my example, the line x, comma, x, comma, x is invariant under the group. Right. And that means that this is not an irreducible representation. I should tell you, sometimes people just write like this, irrep, and that means irreducible representation. So this is not an irreducible representation. Okay? Now, it's the usual story. So we're talking about whether a representation is irreducible or not. Okay? And when we ask that, what we're after is that we want to understand basically how to take a group representation and cut it up into its pieces so that each one of these pieces is reducible. It's the usual story. And in that usual story, we have to figure out how to take simple pieces and make them into a bigger piece. How do you take irreducible representations and somehow glue them together to make a reducible one? Okay, so how do you glue together representations? So definition, if I have two representations, let's say that I call them row 1 and row 2. So let's say that row 1 takes G to GL of U1, and row 2 takes G to GL of U2. Then I want to glue these together. Okay. Now, again, you can think that you're thinking of this as given a matrix for each one of these guys. And so you're giving, I don't know, let's say that this is dimension n1, and this is dimension n2. So you can think that this first representation is like given an n1 by n1 matrix for each group element, and this one is like given an n2 by n2 matrix for each group element. And now somehow you want to put these matrices together. Okay. And I think that there's only one reasonable way of doing that. Well, maybe there's not just one, but there's the simplest way of doing that, which is just to do the following, and I'm going to call it the direct sum. Where what I want to do is the following. Row 1 of a group element is given by an n1 by n1 matrix. Right? Row 2 of a group element is given by an n2 by n2 matrix. And so I'm going to define row 1 plus row 2 of G. I need this to be a square matrix. I need to build it out of these two guys. I think the most reasonable thing to do is just to glue them together like this. You put the n1 by n1 here. You put the n2 by n2 here. And you put basically zeros here. So that's how you can make a new representation out of these two. Okay. So for example, how do we make a new representation out of this one? Well, I give you a recipe for making a representation out of 2, and here we only have 1, but for example, we could take the direct sum of this with itself. Okay. And so how would I make that? Well, rho plus rho would be going from S3 to GL of C6. And for example, what is rho plus rho of, I don't know, 213? Well, what you're going to do is simply make a 6 by 6 matrix where you cut it up into 3 by 3 blocks. And in these blocks you put zeros, and in these blocks you just put the matrix that you have here. Okay. And zeros everywhere else. Okay. And it's easy to check that this is a representation. Okay. Why? Because if I multiply two matrices that have this shape, if I multiply this times something that also looks like this, then what I have to do is multiply this one times this one and put it in that corner. Multiply this one times this one and put it in this corner, and put zeros here. Okay? It's the block matrix multiplication. So this is the check, basically. Okay. So let's think about this. We have a definition of an irreducible representation. We have a way of starting with small representations and making and gluing them together. And so the statement that we would like to be true is that every representation can basically be cut up into irreducibles. And what does it mean to be cut up into irreducibles? It means that it is a direct sum of irreducible representations. So that's what we're going to prove now. Lemma 2. If G is finite, then every representation of G is a direct sum of irreducible representations. So for example, what that means is that we already saw that this guy is not irreducible. And so I'm claiming that you can split it up into irreducibles. Okay. So what I'm going to do is that I'm going to give you a proof for this fact, and while giving you a proof of this fact, I'm going to show you how to carry it out in this special case. Okay. So proof. Let's suppose, well, let's start with some representation. Okay. Now, if this representation is irreducible, then I have nothing to prove. And so let's suppose that it is not irreducible. Okay. So that means that there must be a proper subspace which is G invariant. Okay. We have some subspace such that group elements send things in U to things in U. Like in this case, we had the line x, x, x. Okay. So let me make a claim. My claim is that I can define U perpendicular, what I think of as the orthogonal complement. And the reason I can do that is because I have an inner product, right? I have a bilinear form here. So I can define this thing to be the vectors in V which are orthogonal to everything in U. Okay? So this is some subspace. And what I'm claiming is that if G fixes U, then G is also going to fix U perpendicular. So this is also G invariant. If U is G invariant, then U perp is G invariant. How do I prove that? Well, what I do is that I take some V in U perp. I take some group element, and I check that GV is in U perp, right? What this means. So how do you check whether something is in U perp? Well, what you do is that you take the inner product with everything in U and make sure that you get 0. So I need to check whether U comma GV is equal to 0 for U and U. Okay? Okay. Well, the thing is, what we know about this form, we know two things. First of all, it's positive definite. Second of all, it's G invariant. Okay? Which means that I can act with a group element and not change the answer. Okay? So what I'm going to do is act by the group element G inverse. I'm going to get the same answer. Okay. And now you see this is equal to V. And what about this? Well, U is in big U, and this is some group element acting on it. Okay. But we know that U is G invariant, so if a group element acts on an element of U, you're going to get something that is in U. Okay. And by assumption, V was in U perp, which means that this is 0. Okay. And so that proves this claim that U perp is G invariant. Let's see this in action over here. So what is this? Let me erase this. What is my claim saying in this example? Well, it's saying that because this line is invariant when I act on it by any of these group elements, then the claim is that the orthogonal complement is also going to be G invariant. Okay. Well, here we're living in Euclidean space. So what's the orthogonal complement of this thing? Well, it's this plane the things that are perpendicular to the all ones vector are, the things such that the dot product, which is x plus y plus z, is equal to 0. Okay. My claim says that because this guy was invariant under G, this guy is also invariant under G. And if you look at this, of course it's invariant under G, because what does the group do here? The group just switches the coordinates around. Okay? So if you have some points such that x plus y plus z equals to 0, and you mess up the order of the coordinates, but you don't change their values, then when you do that, you're not going to change the fact that their sum is 0. Okay? So this is also invariant under S3. Okay. So that's the claim, but I haven't proved the lemma yet. By the way, we should do something. We should discuss something, because what I'm trying to say is that any group representation is a direct sum of irreducibles. Okay? And in particular, I want to do this for this example. So I would like to prove to you that this representation is a sum of irreducibles. Okay? Now, what did I say? Well, I said that the way that you sum two representations is by putting them in this block form. Okay? And so one thing that we might like to see is whether we're able to write each one of these things as a block form, like maybe like this. So that we have some matrices here, and we have zeros here. So can we get them to look like this? Well, this one has this form. This one has this form. This one doesn't have this form. Okay. So then what do I do? Well, we're gonna see what we're gonna do, but
You mean it has the upper left hand has a single element up there? Or?
yeah. So what I mean is that if, for example, if I wanted to write this representation as the direct sum of a representation of dimension 1 and a representation of dimension 2, then I would need to get the matrices to look like this.
Because otherwise, if you just turn that around, you get the 2, 1, 3.
Right. But somehow I cannot do this compatibly for all of these 6 guys in this way. Okay? And so we're going to have to do something different. We're going to have to choose different matrices, because, and what does it mean to choose different matrices? It means to change the basis. Okay? So what I need to prove to you is that with some basis in mind, I can do this. Okay? But we're going to see that actually that's almost done. The thing is this. The thing is, here's the claim. We have V, right? We have a representation on V, and we need to choose, if we want to talk about this in matrix form, we need to choose a basis for V. Okay? So choose a basis for V in the form, let's say, I don't know, E1, E2, EK plus 1, En. But I have complete freedom over which basis I choose, and I'm going to choose it in a way that the first I'm going to choose a basis for U, which is invariant, and then I'm going to choose a basis for U perp, which is also invariant. Okay? And then what is row of a group element? Well, here's E1 up to EK, here's EK plus 1 up to En, here's E1 up to EK, EK plus 1 up to En. And if you think about this, for example, this first column is going to be row of G applied to E1, the first unit vector. E1 is in U, so that means that the answer is going to be spanned by U, and it doesn't need any of these guys, so these are all zeros. Okay? And in general, what you're going to find is that you might have non-zero things here and here, but you're not going to have anything here and here. And this is just going to be whatever rho does in U and whatever rho does in U perp. Okay? And so when you do it in this way, you find that basically rho is the representation restricted to U, direct sum with the representation restricted to U perp. Okay? So we'll do that in that example over there. But you see what I'm saying here is that if your representation was not irreducible, then you can write it in terms of two smaller ones. And then you see, okay, are these irreducible? If they are irreducible, you're done. If one of them is not irreducible, then you can repeat this and split it up into two smaller ones. And by repeating this, you're going to get your decomposition. Again, maybe this is clearest if I do it in this example. Okay. So the thing about this, the reason that these matrices don't look compatibly of the same block form is just that I chose the wrong basis. Okay. How do I choose the right basis? Well, first of all, what basis did I choose? Well, this is just the standard basis E1, E2, E3. But I want to choose a different basis, a basis that is compatible with these things which are invariant, right? So I said that the way that I choose a basis for V is first I choose a basis for this guy, and then I choose a basis for this guy, okay? So let's choose a new basis for C3. So new basis for C3 is given by first a basis for this guy, well, 1, 1, 1, and then a basis for this guy. So I can do this in different ways. Let me do it compatibly with how I did it in my notes, which is like this. So I claim that if now I write my representation matrices, if I write my linear transformations in terms of this basis, then they're all going to be of the right form. They're all going to be exactly how I drew them here. You're going to have things here and here. And they're going to have zeros here. And I'm so confident of that I'm going to let you choose one of these 6 group elements, and we're going to do it, and we're going to get it right. 3, 1, 2. Okay. But you have to help me not make a mistake here. So 3, 1, 2. It takes in the normal basis, it takes E1 to E2 3, 1, 2 takes E1 to E2, E2 to E3, and E3 to E1. Okay. So what we have to do now is figure out what it does to F1, F2, and F3. So what does this thing do to F1? Well, F1 is E1 plus E2 plus E3. And this is a linear thing, so we just figure out what it does to E1, to E2, and to E3. And so we get F1. So that's looking good so far, because I wanted it to be F1 plus 0 times F2 plus 0 times F3. What does 3, 1, 2 do to F2? Well, it does whatever it does to minus E1 plus E2. Okay. So what does it do? Well, minus E1 goes to minus E2, plus E2 goes to plus E3. So it's this, but now I should write this in terms of F1, F2, and F3. So how do I write it in terms of them? Carefully. I guess that's F3 minus F2. Okay. And again, that's good because I didn't want it to involve any F1s. I want it to be 0 F1, something F2, something F3. And what about 3, 1, 2 of F3? Well, F3 is equal to minus E1 plus E3. Minus E1 goes to minus E2. Plus E3 goes to plus E1. And so what I get is E1 minus E2, which is minus F2. Okay. So that means that if I write this matrix, if I write the matrix for this operation in terms of F1, F2, and F3 as a basis, then I get a different matrix. The matrix that I get looks like F1, 0, 0, then 0, F1 minus 1, F2, plus 1, F3, and then 0, F1 minus 1, F2, plus 0. And that is the form that I wanted to have. Now, of course, this shouldn't be surprising because I proved this was going to happen, right? But it's nice to see it in an example for some peace of mind. Okay? And you do it for each one of these guys, and you find that they all have this form. And so, basically, rho decomposes into some rho 1 plus rho 2, where if you think about it, rho 1 is pretty trivial. Okay? Because what is rho 1? Well, we're going to look at only the number that we see right here. But if you think about this, no matter what permutation we chose here, we were going to get F1 here. And so that means that no matter which one of these guys we have here, we're going to have a 1 in the top corner. And so this rho 1 is a very silly representation. All it does is to each group element, it assigns 1. Okay. So rho 1 goes from G to GL of C1, and all it does is it takes a group element and it sends it to the number 1. Okay. And rho 2 is something from G to GL of C2, and it does something. It does whatever these guys do. Okay. And you can easily check that this actually is irreducible. And so this is the irreducible decomposition of rho. So I should tell you that basically this is what representation theory is about. Okay? And a lot of the game of representation theory is first to prove, I mean, listen to the representation theory of finite groups, you have this result, okay? And then if you want to understand all the different representations of a group, then it's enough to understand the irreducible ones, okay? And that's a beautiful question that has beautiful combinatorics. So for example, in the case of the symmetric group, it's a beautiful answer. So it turns out that the representations are just very nicely understood. If you've ever heard of this whole theory of Young tableau, it's basically about these representations that are indexed by partitions. And so, I mean, this is a whole topic that I really would encourage you to learn about because it's very interesting. But this is almost all we need. We need a couple more facts about this. But this is pretty much all we need to prove what we're trying to prove, which is that if we have a finite group, then the bilinear form is going to be positive definite. And we're going to use the representation theory of that group to prove that. Okay? All right.
How general is this setup? So the all ones vector is always going to be.
This is the representation for any group. The representation that takes every group element in a sense to 1. Because that doesn't specify something.
But does Sn generally break down this way? So we see an all ones vector and then these kind of pairwise basis vectors. But
that's a good question. So these things have names which escape me at the moment. I think this is just called the trivial representation, and this is called like the standard representation, maybe. And I actually can't remember how this decomposes into. Certainly, it always has this component.
Right.
In general, I don't think that the row 2 you get this irreducible, and then you have to figure out how to decompose it. And I think it just depends on it.
Because that F1 is exactly the kernel of the boundary map for the complete graph on 3 vertices. Guys like this form a basis of the tension space.
I mean, a lot of maybe you've seen this work of Biggs, for example. So he really studies these points of this chromatic polynomials and things like this by just translating everything to representation theory. And it might be similar to